Good evening.
Good evening, sir.
Okay, let's start second syllabus with mechanical property of solids. Let me define you some property. First, suppose you have any support from which a spring is connected having length L up to this point. Now, if you apply any deforming force to this particular spring to stretch it or compress it, so it will become like this, or it will like this. This is your actual position. A deforming force is applied along this direction to compress it. And for this part, along this direction to stretch it. So now there is a property in this particular spring by which a force will develop into it along this direction in this part and along this direction in this part, which will tend to bring back this particular spring up to its original state or original configuration. So this force which get developed into it due to this deformation is called restoring force, and this will be also restoring force. So this particular spring having a tendency by which this restoring force get developed into it due to deformation of spring and compression or expansion. This tendency of a spring is called elasticity. Is it clear?
Yes, sir.
Similarly, solid behaves suppose any solid in which each vertex of cube is occupied by atom to form this crystal. So this will be atom. And bond in between them behaves like a spring. So it will be like this. So if you apply any deforming force to any one side to deform it, let's say along this direction, to stretch it up to this point. Now there is tendency of this solid to develop a restoring force along this direction, which will tend to bring this deformation back to its original state. This tendency of body by which if you remove deforming force, object will have tendency to regain its original state is called elasticity. Is it clear?
Yes, sir.
So elasticity is the tendency of a body to regain its original shape on removal of deforming force is called elasticity. There is one more property related to this or opposite to this, which is called plasticity. Suppose there will be some object on which if you apply deforming force, then object will have inability so that they can't regain its original state on removal of deforming force. Those bodies are called, or those tendency of body are called plasticity. So plasticity is opposite of this elasticity. So you'll say the inability of a body so that they can't regain its original state or shape on removal of deforming force. It's called plasticity. Asma, is it clear?
Yes, sir.
Now, in general, there is no any object which is perfectly elastic or perfectly plastic. So behavior of body would lie in between elastic and plastic. So you'll say behavior of body lies in between elastic and plastic. Is it clear to all of you? Or do you have any doubt? Just write it down. Yes, Mohiuddin? Do you have any question?
Done, sir.
Done, sir. Sir, I have a doubt. Sir,
Yes.
my doubt is in in objects that show plasticity, partially, but they do show plasticity, right? Is there a restoring force that's formed? Because not all objects are totally plastics or totally elastics. Is there a restoring force in these kind of objects as well, but less
Yeah, it will be lesser in amount.
than the magnitude
But
of
in
the
all object,
this
magnitude
answer?
of elasticity will be smaller as compared to plasticity.
Thank you,
But
sir.
in all object, both these property will lie. It depends upon which of these will be larger in magnitude. You all have written?
Yes, sir.
Yes, sir.
Arslan?
Yes, sir, done.
Okay. Mohiuddin, do you want to ask something? Now, the next term is, on the basis of this deformation, we may define some term. First is stress. Suppose you have a body which is hanged from any support like this, having original length L and area of cross section A. Now, if a deforming force is applied along this direction, deforming force, due to which this rod may get slightly stressed to this point. So this deformation is called delta L. So first is a stress, which is the amount of deforming force applied on a body per unit area is called stress. So stress is the amount of deforming force applied on a body per unit area. So stress equals to deforming force divided by area of cross section. Force having unit Newton, area of cross section having unit meter square. So its SI unit will be Newton per meter square, and it will be scalar quantity. Is it clear?
Yes, sir.
Now, due to this deformation or this application of this deforming force, object may get slightly deformed by delta L in this case. In some other case, it will by some amount delta V and some other deformation. So we may define some other term which is called strain. So strain is basically the amount of deformation produced or developed in a body with respect to its original configuration or original shape. So it is the amount of deformation developed in a body per unit its original shape or original configuration is called strain. So strain is basically ratio of deformed shape to the original shape. So strain equals to deformed shape divided by original shape. In this case, deformation is delta L and original configuration of body is L. So it will be delta L divided by L. Now, in both numerator and denominator having same unit, so it will be a unitless quantity. Is it clear?
Yes.
Yes, sir.
Gloria, any doubt? Safan?
Yes, sir.
Okay.
Sir, the deforming phase is delta L.
Yeah.
Okay, sir. Done, sir.
Done, sir. So could you please repeat the definition of strain?
Strain is basically calculation of amount of deformation with respect to its original configuration. So it is just a ratio. So the amount of deformation developed or produced in a body per unit its original configuration or original shape. You all have written?
Yes, sir.
Asma? Done? Sabita?
Yes, sir.
Okay. Now there is a relation between stress and corresponding strain, which is defined by Hooke's law. But there will be two different condition or limiting condition. First, temperature of body or surrounding should be constant, and stress and strain would be within elastic limit. I will define you later what do you mean by elastic limit. So Hooke's law states, if you apply stress to a particular object, strain get developed into it, and they should be proportional or directly proportional to each other. Means the more you apply stress to a particular object, the more strain will develop or produced into it. If temperature is constant, so let's say at constant temperature, and within elastic limit, the strain produced in a body is directly proportional to the stress applied. So stress applied is directly proportional to strain produced. So if you replace this proportionality sign by any constant term, so it will be stress equals to some E times strain, where E is called modulus of elasticity. So if you rearrange this equation, you will get E equals to stress divided by strain equals to E. So this E is called modulus of elasticity, which depend upon two factors. First is temperature, and second is nature of material. It will define you the elastic behavior of body. So greater the value of modulus of elasticity, it means object will have more elastic or object will be more elastic. So first, modulus of elasticity, it defines the elastic behavior of body. Next, it depends upon nature of material and temperature. but it will be independent of dimension. Is it clear till this part? Is it clear to all of you? Or do you have any doubt? Okay, first write it down.
Done, sir.
Done, sir.
Mariaz, do you want to ask something? Or is it clear? You all have written?
Yes, sir.
Now, since stress applied is directly proportional to strain produced or developed into it, so due to this proportionality, you may define curve or graph stress versus strain. Since these two are proportional to each other, so graph will be a straight line like this, which is inclined at some angle theta with respect to this x-axis. So according to this relation, it will be slope of stress strain curve will define you modulus of elasticity, which means E equals to tan theta. Is it clear?
Sir, could you explain once again?
Since stress is directly proportional to strain, so graph between stress and strain for any material within this condition at constant temperature and elastic limit should be a straight line passing through origin, and which must be inclined at some angle theta with respect to x-axis. So we may rearrange this equation like this. So it is nothing but perpendicular by base, which is equals to tan theta, or which is equivalent to slope of this particular graph. So you'll say stress strain curve or slope of a stress strain curve will define you modulus of elasticity, which is equals to tan theta related to this graph. Is it clear now?
Yes, sir.
Next is, you may ask how modulus of elasticity will depend upon temperature. So just remember, modulus of elasticity will be inversely proportional to temperature. If you increase temperature, particle or separation particle increases, due to decrease in bond strength. That's why elasticity of body will be decreases. So elasticity will be inversely proportional with a rise in temperature. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Done, sir.
Aslan, you have written? Asma, done? Now, on the basis of these three different terms, we may define its type. Types. First, suppose you have a rod if a deforming force is applied along this direction, and in this part, it will be along this direction, due to which deformation in these two terms will be along this direction. In this part, original length is L, and deformation from this point to this point is delta L. Similarly, in this part, it will get compressed slightly to this part by delta L. Original length is M. So this particular first term, since it is elongation, will be termed as longitudinal or tensile. In second part, it is getting compressed, so it is called compressile. So all these terms are similar, they are only differ in direction. So first, longitudinal stress. So it will be amount of deforming force applied, that is F, divided by area of cross section E. Similarly, amount of deformation produced is called longitudinal strain. So amount of deformation in this is delta L, divided by original shape is L. And the ratio of these two terms by Hooke's law is called modulus of elasticity. For this longitudinal section, it is called Young's modulus. So Young's modulus equals to longitudinal stress divided by longitudinal strain. Young's modulus is denoted by Y. Longitudinal stress is force divided by area of cross section, whole divided by longitudinal strain, that is delta L divided by L. So on rearranging, it will be F times L divided by A times delta L. Since this particular deformation is along length, so this Y, that is Young's modulus, is also called elasticity of body in length. And next, since strain is unitless quantity, so Young's modulus will have same unit as stress. So SI unit is Newton per meter square. And it will have all property of modulus of elasticity, which I have defined above. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Answer.
You all have written? Arslan,
Done, sir.
Aisha?
Done, sir.
Okay. Asma, any doubt? Suppose a wire having length 2 meter, area of cross section is 4 mm squared, is hanged vertically a force of 20 kilonewton is applied at its end to elongate it. Find first amount of stress applied, amount of strain produced if Young's modulus equals to 2 into 10 to the power 11 Newton per meter square. And third is delta L produced. Just use the above formula and try to simplify it. First, try to write each term in their SI unit as given in the question. Suppose we have length as 2 meter, which is in SI unit. So L is equals to 2 meter. But area of cross section is 4 mm square. So multiply it by 10 to the power minus 6 to convert it into meter square. Next is force applied, which is in kilonewton. So multiply it by 10 to the power 3 to convert it into Newton. And last, modulus of elasticity or Young's modulus is 2 into 10 to the power 11 Newton per meter square. Just use these values. Try to simplify. Mariam, just check your calculation. Sumaira, just check your calculation. Good, Sabita. Muhyiddin, just check your calculation. Let me solve. As stress equals to force divided by area of cross section. Force is 20 into 10 to the power 3 divided by area of cross section 4 into 10 to the power minus 6. So 4 in 5 times will be 20. And we have 10 to the power minus 6 in denominator. So if you move it to numerator, it will become plus. So 5 into 10 to the power 3 into 10 to the power plus 6. So on combining, it will be 5 into 10 to the power 9 Newton per meter squared. Good, Samira. Is it clear?
Yes, sir.
Maria, is it clear?
Yes, sir.
Try to find the second part. Good, Asma. Mariam, just check your calculation. Safan, send your answer. Arslan. As we have Young's modulus equals to stress divided by strain. So from this, strain equals to stress divided by Young's modulus. The stress we have already calculated as 5 into 10 to the power 9 divided by Young's modulus, which is 2 into 10 to the power 11. So it will be 2.5 into 10 to the power. We have 10 to the power 11 in denominator. So on moving to numerator, it will become minus 11. So 9 minus 11 will be minus 2. And strain is a unitless quantity, so it will be as it is. Mariam, is it clear?
Yes, sir. Sir, we cannot use the strain formula.
Since we don't have delta L in this given.
Yes, sir.
For third part, strain equals to delta L divided by L. We have strain and L. So from this, we can calculate delta L. So delta L will be equals to L times strain. L equals to 2 meter and strain produced is 2.5 into 10 to the power minus 2. So it will be 5 into 10 to the power minus 2 in meter. So if you convert it into centimeter, it will be just 5 centimeter as delta L. Good morning. Samira, is it clear?
Yes, sir.
Aisha, any doubt? You all have written?
Yes, sir.
Yes, sir.
Suppose you have support like this. Wire is hanged, then a block, another identical wire, and then block. This is of 2 kg and this is 3 kg. If wires are identical, find the ratio of stress in each wire. Wires are identical means length and area of cross section of them should be equal. Mariam, just tell me how to approach this problem. First, we have to calculate stress. So we need two different terms. First is amount of deforming force, and second is area of cross section. So in this particular system, which is responsible for applying deforming force to this entire part?
Gravitation.
Good. Acting on the block. So for the lower part, since mass of block is 2 kg, so there will be force 2 times gravity in downward direction, which develop a tension in this particular string as T1. So total upward force should be equals to total downward force. So T1 equals to 2 times gravity. Is it clear?
Yes, sir.
Similarly, at this point of contact, there will be tension in downward direction as T1. As for massless and inextensible string, tension will be same at each point, and it always acts opposite to the point of contact. So this T1 will be in downward direction. Next is mass of that block is 3 kg. So there will be another force due to gravity in downward direction. That will be mg, that is 3 times gravity. And in opposite of it will be a tension T2. So net force acting on this particular part will be 0. So total upward force equals to total downward force, and it will be equals to 5 times gravity. This particular tension acting on this particular string will be responsible for applying deforming force to them. Is it clear?
Yes, sir.
So stress in first part equals to tension in first divided by area of cross section. Stress in second part equals to tension in second divided by area of cross section. Now just divide them, put the value of T1, T2 and simplify it. Asma, is it clear? Samaira,
Yes, sir.
Arslan, any doubt?
No, sir.
Good, Sabita. Good, Mariam. Asma, just check your calculation. Good, Samaira. we have T2 equals to 5 times gravity. Good. Safan, is it clear?
Yes.
Send me your answers. Aisha? A and A will cancel out. So you will get T1 divided by T2. T1 is due to 2 times gravity and T2 is due to 5 times gravity. So G and G will cancel out. So you'll get 2:5 or just 0.4. Now this particular question may be asked like this. If you define tension at this top point, it will be along this direction as T2. So you may resolve this particular part as horizontal. We have a block like this and another like this. This will behave as top surface, and there is one force at this point along this direction, which is of 2 times gravity. There's one at this point along this direction, which is 3 times gravity. And at this point, opposite of it will be 5 times of gravity. So let's say this is first string and this is second string. So you may be asked this particular problem like this way. So first of all, just try to write this particular problem in vertical part like this, and then apply this concept to find a relation of stress, strain, or Young's modulus. Is it clear?
Yes, sir.
Next is tangential or shear. Suppose you have a cylinder whose base is fixed and tangential force is applied at its top along this direction F, by which it gets slightly deformed along this direction like this. So there is bending from this point to this point. Let's say X, length of cylinder is L, and bending by some amount theta. So this force is applied on the surface tangentially to bend it by X amount. So stress or shear stress equals to F tangential applied per unit area of cross section. Corresponding deformation is shear strain, which equals to theta x by L. And the ratio of these two terms, which is modulus of plasticity, in this term it is called shear modulus, which is equals to ratio of shear stress and shear strain. Shear modulus is represented by capital G equals to F tangential divided by area of cross section whole divided by theta, or it is equals to F tangential into length divided by A times X. Now this G is basically in this part, due to application of force, there is change in shape. So this G or shear modulus will define you elasticity in shape of body and will have same unit Newton per meter squared. Is it clear?
Yes, sir.
Done, sir.
You all have written?
Yes, sir.
Aisha?
Yes, sir.
Suppose a cube of side 10 centimeter whose base is fixed. A tangential force of 2 kilonewton is applied to its top face. Find first stress, second shear strain, if G is equals to 4 into 10 to the power 8 Newton per meter squared. Try to solve. Try to solve. Yes, Mohiddin. Force is 2 kilonewton. Yes, Mariam. Asma, just 1 minute, I'm checking. Asma, you have done a little mistake. We have side of cube as 10 centimeter, which is not in SI unit. So we have to convert this particular term first in SI unit and then apply the formula. So area of top surface will be length square or side square. So it will be 10 divided by 100, 10 divided by 100, or it is equals to 10 raised power minus 2 meters squared. Force is 2 kilonewton. So it will be 2 into 10 to the power 3 Newton. Now apply the formula. Good, Mohiddin. Good, Maria. Good, Samira. Sabita, send your answer. Safan, Asma. Good, Asma. Good, Mohiddin. So shear stress equals to force divided by area of cross section. Force is 2 into 10 to the power 3 and area is 10 to the power minus 2. So it will be 2 into 10 to the power 5 Newton per meter squared. Next is shear modulus equals to shear stress divided by shear strain. So strain equals to stress divided by shear modulus. Stress equals to 2 into 10 to the power 5. Correspondingly, G equals to 4 into 10 to the power 8. So it will be 0.5 into 10 to the power minus 3, and it will be unitless quantity. Aisha, is it clear?
Yes, sir.
Arslan? Okay. Third type in this term is about volumetric, or it is also called hydraulic. Suppose you have spherical body on applying force from all sides, there is deformation in its volume so that it will get compressed to this part. Now it will be up to this. As this force is perpendicular to the point of contact to the area, so it is called pressure also. So first, volumetric stress equals to force that is perpendicular to the surface per unit area. So it is also called pressure. Change or deformation produced is volumetric strain. So it will be equals to change in volume divided by initial volume. Since initial volume is greater as compared to its final volume, so change in volume equals to V final minus V initial. So it will be negative. So here we'll have negative sign. Now the ratio of these two terms will, or that is modulus of elasticity. In this term, it is called bulk modulus, which is equals to volumetric stress divided by volumetric strain. So bulk modulus beta equals to pressure divided by delta V by V with negative sign, or it will be minus of P into V divided by delta V. Is it clear?
Yes, sir. Done, sir.
Asma, just write it down first. I'm explaining you again.
Sure, sir.
Done, sir.
You all have written?
Yes, sir.
Since in this part, to deform from all of its side, this force, or this force, or this force applied over this particular object would be always perpendicular to its point of contact. So force perpendicular to that surface is also called thrust, and thrust per unit area is also called pressure. So hydraulic or volumetric stress equals to perpendicular force acting per unit area. So it is also termed as pressure applied over that particular object. Asma, is it clear? Now, since this particular deformation, initial volume is larger as compared to its final volume, since it is decreasing. So difference of these two terms will be negative. So volumetric strain equals to minus of delta V divided by V. Now on taking the ratio of these two terms, it will be volumetric stress divided by volumetric strain. So volumetric stress is pressure, volumetric strain is delta V by V. So move this V to numerator, it will be minus of P into V divided by delta V. Volumetric strain or strain is a dimensionless quantity. So dimension or unit of bulk modulus is Newton per meter square, or it will be just Pascal, which is equivalent to pressure. Mohiuddin, is it clear? Now there will be a question related to this. If a pressure of 20 atm is applied on a spherical body so that percentage decrease in volume is to find beta. First, volumetric stress. Second, volumetric strain. And third, bulk modulus. One atm pressure equals to 10 to the power 5 Pascal. Just use this conversion. Let me give you some hint how to approach this problem. In this, we have application of this force. So volume is decreased by 2%. As percentage change means delta V, or change in that quantity, divided by its original volume multiplied by 100 is percentage change in volume, which is equals to 2. So we have to find only delta V by V. So just move this 100 to the other side. So it will be 2 divided by 100, or 2 into 10 to the power minus 2. Since volume is decreasing, so they have negative sign and negative sign. Now apply the formula and try to find. First, pressure is 20 atm. So P equals to 20. 1 atm equals to 10 to the power 5. So just multiply it by 10 to the power 5. You may write it as 2 into 10 to the power 6 Pascal. And this pressure is also equals to volumetric stress. So volumetric stress equals to 2 into 10 to the power 6 Pascal or Newton per meter square. So this will be your first answer. Next is volumetric strain, which is equals to delta V by V with negative sign. So if you put this value from this, minus and minus will cancel out. So you will get 2 into 10 to the power minus 2, and it will be unitless quantity. Is it clear, Mariam?
Yes, sir.
Now just divide these two terms to get beta or bulk modulus. Try to solve. Asma, is it clear?
Very clear.
Good, Samaira. So if you divide these two terms to find beta, it will be equals to volumetric stress divided by volumetric strain, which is equals to 2 into 10 to the power plus 6 divided by 2 into 10 to the power minus 2. So 2 and 2 will cancel out. So you get just 10 to the power 8 Newton per meter square or Pascal. So Fan, any doubt?
No, sir.
You all have written?
Yes, sir.
Yes, sir.
Sabita?
Yes, sir.
Okay. Now, the next term is for perfectly rigid body. Suppose if there exists a rigid body or perfectly rigid body, which means there will be no deformation produced in this part. So delta L will be equals to 0, delta V equals to 0. So if you put this value to find modulus of elasticity, let's say for Young's modulus, which was F times L divided by A times delta L. So if you put delta L to be 0, so this will be 0. Any number divided by 0 will be infinite, which means modulus of elasticity or Young's modulus will be infinite. So just remember, for perfectly rigid body, Young's modulus, shear modulus, or bulk modulus will be infinity. Is it clear?
Yes, sir.
Next is you will be asked to prove something. Which is more elastic? First, steel and rubber. Second, water and air. You'll have to prove this particular term mathematically. So let me define you how to approach. For first part, suppose there is a support by which a fixed length of rubber and steel is fixed. Let's say this is rubber. Next is steel. I have taken both as identical to each other in terms of length and area of cross section. Is it clear?
Yes, sir.
Now, if you apply any deforming force or constant deforming force to both of them, let's say first for rubber, and steel. In which of these two you will supposed to get maximum deformation?
Rubber.
Good. So it will be in rubber. So amount of deformation produced in rubber will be more as compared to steel. So this is delta L in rubber and this is delta L in steel. So you'll say on applying same deforming force on identical segment of rubber and steel, delta N in rubber will be more as compared to delta L in steel. And as we know, Young's modulus is inversely proportional to deformation. Young's modulus equals to F times L divided by A times delta L, which means inversely proportional to delta L. So greater the value of deformation, it will have smaller Young's modulus. Therefore, Young's modulus in rubber will be smaller as compared to steel. So greater the value of modulus of elasticity, it means it will be more elastic. Hence, steel is more elastic as compared to rubber. Is it clear?
Yes, sir.
Aslan, any doubt?
No, sir.
Muhiddin? You all have written?
Yes, sir.
Similarly, for water and air, since these two are fluid, so we can take, let's say, in a balloon for equal volume. One is, let's say, water, and the other is gas. So for volumetric stress or hydraulic stress, if you apply same pressure on both of them, this and this, In which of these two you will supposed to get more amount of deformation or change in volume?
Yes.
Yes.
So it will be slightly compressed. But in this part, it will be longer. So you will say on applying same pressure for equal volume of water and gas. Delta V in gas will be more as compared to delta V in water. And since bulk modulus is inversely proportional to change in volume, therefore beta in water will be more as compared to gas. Hence, water is more elastic. Is it clear to all of you
Yes, sir.
how to prove these type of questions? You all have written?
Done, sir.
Safan, you have done? Arslan?
Yes, sir.
Suppose you have stress versus strain, and there is two different material. First is A and second is B, for which inclination is 30° and 60°. Find ratio of modulus of elasticity for two. As I have defined you earlier, modulus of elasticity in terms of graph will be equals to slope of it. So try to find slope of A and B and take ratio of them. Suppose for A, whose inclination is 60 degree, so you will say modulus of elasticity of A will be tan of 60 degree. Similarly, for B, modulus of elasticity equals to inclination of B is 30 degree, so it will be tan 30. Now put the value of these two terms and divide it to get ratio. Try to solve. Good Muhiddin. Good Mariam. Sabita, just check your calculation. Good Samira. Asma, send your answer. Arslan, Safan. Asma, check your calculation. Tan of 60 degree equals to just root 3. And tan of 30 degree equals to 1 by root 3. So on dividing these two terms, root 3 will move to numerator. So it will be EA divided by EB equals to root 3 into root 3 divided by 1. That will be 3:1. Is it clear? Sabita?
Yes, sir. I understand.
Okay. You all have written?
Yes, sir.
Okay, so let's stop here for today's. In next class, I will define you one last part of this chapter, which is potential energy stored in a wire. Okay. So do you have any doubt from today's class? Asma?
No, sir.
Okay, then just revise this whole part. Try to do more and more problem. In next class, I will continue next. Okay.
Thank you, sir.
Thank you. Okay, thank you.
Recording in